Today I'm going to do the 2007 presentation on the 2007 Hyundai Elantra 2-liter 4-cylinder engine. So just a quick intro is it's a 4-cylinder 2-liter engine, and it's an inline 4 type engine, and it has a horsepower of 138 at 6,000 RPM and has a torque of 146 pound-feet at 4,600 RPM. It has a compression ratio of 10.1, and its fuel type is just regular unleaded 87 octane gasoline, and its max RPM is 6,000. So this here over here on the right is just a picture of the combustion chamber that's used in the engine, just a general picture I found online because I couldn't get a picture of it within my actual engine. And its configuration, once again, is an inline 4-cylinder engine. Its compression ratio is 10.1 to 1. And its displacement is 2 liters, and its peak cylinder pressure is 91.6 ATM to 114.5 ATM. And it's constructed mostly out of aluminum and cast iron because it's meant to be a lightweight, fuel-efficient vehicle. So obviously the lighter the engine is, which is the heaviest, sometimes the heaviest, one of the heaviest parts of the car. If the engine is lighter, it's obviously going to make the vehicle lighter, which will make it more fuel efficient. So just here's a quick picture of the fuel system. So you can see here, I can't move the camera. Let me go back. All right. So right there is the fuel filter, the fuel tank, the fuel pump, exhaust system, and the fuel line. So obviously like I said before, it uses regular unleaded gasoline that is 87 octane, and it's designed for adequate performance but optimal fuel efficiency. It uses a multi-point fuel injection system, operates under standard pressure. The system provides precise fuel metering as well as fuel injectors that are placed in order to optimize fuel automation and air mixing with the combustion chamber. And it operates, and obviously it's standard pressure, it operates at 54 to 58 psi, which is the vehicle's standard pressure. 58 is the max, and it has to be at least 54, be within that range. The fuel injection nozzle is designed to deliver fine droplets around 15 to 25 microns is the approximate size, and it provides a fuel flow rate calibrated to match the engine's 146 pound-feet torque output at 46 RPM. So just to have under the vehicle operating under standard pressure, the system just provides the fuel metering so it can have optimal combustion, and it improves the efficiency. And then for the precise fuel metering, it's meant for also optimal combustion and improving efficiency as well as reducing emissions. And just in general, and then the fuel nozzle is designed to deliver fine droplets, delivers around 15 to 25 microns, and the fuel injector nozzle sprays a fine mist directly to go through the process, sprays a fine mist directly into the combustion chamber of the engine, and it's just very crucial for the mixture and the combustion. And then while optimizing the combustion, the nozzle is designed to deliver fuel droplets at a specific size to ensure the efficient mixing with the air, promoting complete combustion and optimal engine performance. And the next slide is the ignition system. So up here, just two pictures just found online. That's the entire set, and that's just the one part for the ignition system within the vehicle. So the ignition system in this Elantra includes a standard spark plugs like every other vehicle, and it uses electric timing controls that ensures that the spark plugs occur at an optimal point within the combustion cycle. The ignition system is also specifically designed to work with 87 octane fuel and is essential for the efficient combustion, and it coordinates closely with the fuel delivery system and engine timing. So the ignition system in a 2-liter engine is electronically controlled by an engine control unit, which, as you can see, the engine control unit it's based on various engine parameters like engine speed, load, and temperature is what it reads to get what it needs to. And just for the ignition timing, it can be adjusted. The ignition timing can be adjusted within 1 to 2 degrees, adjustable depending on the engine load and RPM. And the system design reduces the misfiring within the engine. So when the engine is misfiring, it obviously tends not to run the same, and it can also cause damage within the engine, and it can cause it not to run properly. And it uses coil-on plug units just for each cylinder within the engine and the combustion cycle. And the ignition timing can be, obviously, I said before, adjusted within 1 to 2 degrees. The spark plugs also have a gap of 0.052 inches, also 1.32 millimeters, which is very critical because without that, it's very optimal for the spark plug and the combustion cycle of the engine. and it's this these ignition systems are capable of handling engine speeds up to 6,000 RPMs without the vehicle starting to lose its reliability. The air intake rate is 250 to 300 liters of air per minute at a maximum RPM. At the maximum RPM. So the valve train and cam. The valve train uses a dual head overhead camshaft setup, which you can see in the picture right here on the right, which allows for more precise control of the intake and exhaust valves. The design enhances the engine's ability to breathe, which will give it more efficiency at higher RPMs, and it's just good for maintaining the power output. So here's use a dual overhead camshaft, which increases the airflow and its overall performance. It also uses a timing chain instead of a timing belt, and having a timing chain that lasts a little bit longer, and it lasts up to 130,000 to 150,000 miles on average, which is a very long lifespan for a car. So you'll very unlikely have to repair it unless you're riding the car until it dies and you want to keep the car going. And it uses 4 cylinders. There's a 4 valves per cylinder within the engine, just to improve the process in general of the combustion. And the valve variable timing adjusts the timing of the intake and the exhaust valves within the engine. And the camshaft dimensions are just to give some dimensions of some of the things in that picture. It's 0.0394 inches or 8 millimeters to lift the cylinders at higher RPMs. And the assembly of the entire combustion system, the entire valve train and cam, is 20.6 by 4.1 by 4.1 inches. So for the intake and exhaust system, this is just, I couldn't really get a picture of it, obviously, so I found like a little diagram online. Can I move this? I don't think I can. So if you can see, mostly in this picture here, it's just a bunch of part numbers and just the overall like assembly part by part, just fully in a zoomed out, spread out view of what the entire system looks like. So the intake system contains an air filter, uh, air intake ducts, intake manifold, throttle body, and a mass airflow sensor, intake air sensor, and an intake resonator. It delivers about 200 or 250 cubic feet per minute when it has a max airflow. For the air filter, the intake begins within the air filter. This is obviously step by step with where it goes. The air filter removes the dust, the dirt, the pollen, and all the other things that come in from outside the car so it doesn't get into the engine. And then the mass airflow sensor, after passing through the filter, the air of the mass flow sensor uh, measures the amount of air coming into the engine so they can tell other parts what to do. And then the air fuel mixture for combustion has a throttle body that regulates the amount of air entering the engine based on the driver input and the driver pressure at the acceleration pedal. Then the intake manifold distributes the air evenly to each cylinder intake port, ensures that the cylinder receives the right amount of air for combustion process. The variable valve timing may, for some models, are just used just to adjust the valves and optimize performance. The intake resonator helps reduce the intake noise and the airflow characteristics of the vehicle. And the air intake temperature sensor monitors the temperature of the incoming air and monitors the temperature of the engine, just for the air fuel mixture for the optimal combustion. So for the exhaust system, it contains an exhaust manifold, a catalytic converter, exhaust pipe, muffler, resonator, exhaust tip, and an oxygen sensor. For the exhaust manifold, it has typically a diameter of 1.5 to 2 inches for each cylinder exhaust port. For the catalytic converter, it's more for the efficiency, and it has a rating of approximately 90% or 90% efficiency when it comes to reducing emissions like CO, like carbon dioxide, hydrogen chloride, or just stuff like that within the engine. Exhaust pipe diameter is just ranges from 1.75 to 2.25 inches. The muffler noise reduction is just obviously it's just meant to reduce the decibels of just the car while you're revving the engine or just driving in general. Because when the car doesn't have a muffler, in its straight pipe, it tends to be a lot louder. And then the resonator effectiveness, it's just can further reduce the exhaust noise by another 5 to 10 decibels. It's just another thing just to lower the noise of the car. And then the oxygen sensor has an accuracy level of about point plus minus 1%. And the exhaust gas recirculation process efficiency is can reduce emissions by up to 70% just by recirculating the gas back into the engine. And just the stoichiometric point of this is 14.7 to 1. So just to give it talk about the balance performance of it, it has an adequate power with a good balance of acceleration and cruising while driving the vehicle. It has a great fuel efficiency without affecting its performance. Balance handling with the high responsiveness and comfortable ride for both the passengers and the driver. Has all advanced safety technologies within the vehicle. So just to talk about the boost pressure calculation. So here on the side, just some basic things. It uses isotropically heated by isotropically by supercharger, and just some numbers that you use for it. So the HP is 138 here, and then you do that times 2 to get the 276. So the formula is the isotropic relation for pressure and the temperature, and obviously right here, then you just need the double for the pressure of within the engine. So okay, perfect. So the calculated boost pressure of PSI indicates just the additional pressure above the atmospheric level is needed to be provided by the supercharger, and the boost efficiency increases the air density entering the engine, allowing for greater air mass per cycle when matched with correct fuel ratio, and it also significantly enhances the power output. So here's the first picture of the equation and all the variables. And then for the boost pressure calculation, so for T2, you subbed into the isentropic equation, and then you came out to getting 375.48 K for my vehicle. And then we had to calculate the required boost pressure. That's just some of the things you need to do to find the final temperature. You need the ambient pressure, which I did a little bit of research to find the ambient pressure. So it came out to 100.624 because it was approximately 14.6 psi, and it was 100.624 kPa. And then you do that, you multiply that by 2 to get P2, and then you require boost pressure above PATM. The boost pressure is pressure 2 minus pressure 1, and you do that just proves the point before. You go back to having approximately 14.6 psi in order to double the power of the engine. So just talk about some of the engine efficiency and its performance. So to talk about the mean effective pressure, it just represents the average pressure exerted on the piston within the power stroke during the cycle. And it's measured at 11.45 ATM, including the pressure in the power stroke. So to talk about the actual engine thermal efficiency is 61%. And you get that, and that just means that it measures how effectively the engine will convert heat to fuel within the combustion process, and it has just an overall, and it demonstrates a thermal efficiency of 61%. The ideal Otto cycle efficiency is 58%, which is just the model for the spark ignition, just providing the ideal efficiency benchmark for the spark for the Otto cycle. And our engine's Otto cycle is 58%, and it's including the maximum theoretical, attainable efficiency under the ideal conditions for that vehicle. The flame speed at the red line RPM is just the highest engine flame speed that it can measure when it's the engine and the car is at max performance before anything bad starts to happen within the engine. So here's just a video of the car running with the hood up within the engine. If I can get my mouse over here. Y'all. This is me. Slow and then revving it very quick. Just to get the sound, you can see the timing belt there in multiple different parts. The next video is the dashboard for me from the other side while I was revving it. Yeah, you can see my oil lights on. I'll show you yesterday. And it's just revving the RPMs up to see what the car can go to and where it starts to flat out before it shifts to that next gear to get to the next level. I just figured rev it in the driveway and just do it from both sides. for this is just my car going 0 to 40. Just RPM here. You see it has a very slow start and it kind of bottoms out at around 5,000 RPMs and pops back down because it hit the 40 and then it was shifting to the next gear. And this is 0 to 60. See, the car gets to around 40 and it's not very the best getting those higher speeds. To get to 60, it didn't really shift gears. It just topped out at 5,000 RPMs after that, and then shortly after, it dropped back down to 3,500. So obviously, this is a very fuel efficient car. It's meant for good performance, but obviously not speed because it is a 4 cylinder engine with only 2 liter. It's only a 2 liter 4 cylinder engine, so obviously it's not going to have the greatest performance. It's just meant for just just being a good car that can last you a while that is reliable. And here is 60 to 80 on the highway. I was trying to push it, and it was just taking forever. It got me up to like 6,000 RPM, max RPM, and then I kind of got slowly got to 80, and then I kind of flatted out at that. And we're going to explain to you in the next slide exactly what happened to my vehicle. So as you can see here within the video, when I get to about right, yeah, when I get to about right here, you can kind of hear that sound like how the RPM dropped, and I'm still just sitting at 70 miles per hour. I think this is when I pushed my car to its limit. It was already given to go. I think this is right when my transmission kind of blew, and you hear that noise, and it's sitting at 6,000. I'm still hammering the gas, and nothing's happening. It's not shifting gears and going to the next level. So obviously, it was struggling a lot here. Some of these numbers that you get from these videos may not be completely accurate, just because the car is not at its best shape when you first buy it off the market or when there's nothing wrong with it. So it's kind of topping out there. A hammer in the gas, the RPM just in the same. My foot's all the way down on the gas pedal. It's not going any faster. You see here towards the end of the video, yeah, I didn't see it on the video, but it kind of just drops. And then just a quick conclusion. Uh, and yeah. So like some of the transmission problems I've been having with my car recently is just that it tends to just top out at a certain point, and then I kind of get like a jerk back with the vehicle, and it just kind of the car tends to shake. It drops RPMs, my speed drops with it. Then I got to let the car sit and slow down for a little bit for it to start getting holding back again. Because whenever I press on the pedal, when it has like those reactions, it's not all the time. It wasn't all the time, and now it just happens out of nowhere where the car just can't go. So my transmission is going, and obviously it's not really correlating with some of my data and some of my numbers just because of the RPM. So a quick informant conclusion of the car. This is just a picture of the car when I first got it used about 2 years ago. So around 125,000 miles. It was at about 153,000 miles now. So it has an average performance. It's just a very average performance, but gets the job done. It has great engine efficiency, good emission controls, and it just meets the need of when you're looking just for a used car and a sedan. It just meets the need of just being able to last a long time and just having a good cheap fuel economy. So I thought just to add this video at the end. About 2 minutes after that video was taken, on the side of 55, here's because shortly after that, I pulled over to the side of the road after filming that video. This thing is all car. It's not because of the project. It's more the car should not be dying out when you accelerate from 60 to 80, and it just goes. It was the day. It was due. I knew my transmission was going very soon, and about 30 seconds to a minute after that, my car was just sitting at 60. It wasn't accelerating. It started making noises. It started shaking. I kind of felt like a sort of small little smell coming from the engine. So I ended up just pulling over on the side of the road. Happened to me on my way back here to school after Easter. Thought maybe turning the car off and turn it back on would reset it just so I can get to my location and get to a better place to get a tow, possibly. And it just didn't start up. It wouldn't get out of the first gear. The most the car would go up to is 10 miles per hour for like 15 seconds, 10 seconds, and then it just shit the bed and all the lights, dashboard lights turned on and the car just stopped moving. So yeah, that was a fun time yesterday for 2 hours. But stuff happens. Car was due to go, and I knew exactly what the problem was with it. And just here's some of the references.